Cooking. All right, so last time we talked about what's programming, kind of the problem with human beings being so good at programming or so good at problem solving, we have issues articulating the problem. The heavy Milwaukee traffic, I heard it was heavy Milwaukee traffic. Well, except for him. I heard Grand Theft Auto gave you diarrhea. That's what the story was up here. I'm just don't shoot the messenger. All right, so the idea is that humans are so good at problem solving that we have difficulty articulating how we solve problems. So what's the job of a programming language? It's to give us some sort of tool that allows us to not have to change our ways too much, but still be able to talk to a computer. We talked about how human beings solve problems by using our memory, asking questions, and repetition. And we have this slide called the mapping, where every single computer programming language will have facilities for these three things. So memory is usually emulated through something called variables, asking questions through conditionals, repetition through loops and functions and procedures. All right, so then we had several different slides that looked at programming languages from some different angles, like three kinds of programming languages: machine language, zeros and ones; low level, one-to-one relationship with the CPU. What do I mean by that? When I say a low level language has a one-to-one relationship with the CPU, what am I talking about? Say this again?
It only works with the CPU.
Okay. So let's assume that that's not as far off as it sounds like it is. Then what would the difference be with a high-level language? Sure. So we say a low-level language has a one-to-one relationship with the CPU, and a high-level language has a one-to-many relationship with the CPU. So when we say that a low-level language has a one-to-one relationship with the CPU, what does that mean? We talked a little bit last time, well, actually quite a bit last time, about the nature of the CPU, right? So the CPU is kind of like has a whole bunch of magic tricks, right? We look at a hello world program written in for Linux assembly. So when I say that a low-level language, like assembly language, has a one-to-one relationship with a CPU, that means that every line of code in a low-level language translates into exactly one magic trick on the CPU. So we're talking to the CPU on a one-to-one basis. I tell the CPU to do this, it does that. I tell it to do this, it does that. We tell it to do 50 things in a row, maybe something small happens. Whereas in a high-level language, as a programmer, I tell the computer to do something, and it translates that into a whole bunch of instructions to the CPU. So that one directive from me turns into a whole lot of instructions, a whole lot of magic tricks on the CPU. That's a power tool. We like those, right? Okay, so we saw the Hello World program last time written in a low-level language, and that was like, 10, 15 lines of code, something like that, where the equivalent program written in a high-level language would be one line. System.out.println hello world. Done. Even though we know under the hood, all those other lines got generated. They just didn't get written by us. Make sense? All right, so we like these high-level languages, even though we recognize that low-level languages play a part in it, because at the end of the day, before our program actually runs on the CPU, it has to move into a low-level language, which then gets assembled into zeros and ones.
Is there only one type of assembly?
No, because there would be an assembly language for each CPU architecture. So if we look at an Intel CPU versus, if we go back a bunch of years, like a PowerPC CPU, each one of them, while they might have magic tricks that are similar or even sound identical, they have different names associated with them. So they would each have their own assembly language. Then on top of that, the other thing that impacts the assembly language is the operating system that we're running, because we have system calls. Remember we talked about like the syswrite system call last time? So that was specifically a system call that came from Linux. So every CPU architecture for every operating system would then get its own assembly language. Now, most assembly languages are going to look pretty similar. You might find a lot of, for instance, the move command, MOV. Most assembly languages have a move command, but they don't have to. Technically, you could have some different syntax. All right, so there's the CPU stuff we talked about. POSIX. Let's see. So we did talk about how Apple failed and about Next computers. So I think we used you as the guinea pig, right? That he said he never heard of Next computer, and then we realized he's actually sitting in front of one. Just happens to have an Apple logo on it. So Next Computers was the company founded by Steve Jobs while he was canned from Apple, and then they brought him back while they acquired Next Computers, which came with Steve Jobs, and then all of a sudden they started coming out with a whole bunch of stuff that helped Apple get back on its feet. Part of that was the technology that Next Computers came with. We've made a list of what we presumed were some programming languages. So this is nowhere near a full list, but it's a list nonetheless. Here's another angle of looking at programming languages. We have two kinds of programming languages. We have loosely typed and we have strongly typed. So this comes down to how variables work, how we're emulating memory in our programming languages. So loosely typed languages do not require that we label a variable for what kind of value it's going to hold, where strongly typed languages do. Generally speaking, loosely typed languages are relatively slow. Strongly typed languages are relatively fast, but with an emphasis on that phrase relatively, because computers are really fast. So a human being for most applications is not going to notice the difference. Two kind of programming languages, domain-specific and general purpose. So general purpose languages are the languages that we're mostly familiar with. So things like Java and C++ and C# and all those. These are big programming languages that are built to solve a whole bunch of different kinds of problems. A very generalistic classification of problems, as opposed to the programming language that might be on your dishwasher. You know, that only knows how to do a couple of things because when the guy comes out to repair your dishwasher, you know, he needs to cycle it. There's like 4 or 5 things he might need to do. So it just doesn't have to be all that complex. 3 kinds of programming languages. We kind of breezed past functional because it doesn't really mean much to us right here. But procedural versus object-oriented. Procedural languages tend to be monolithic in nature. Object-oriented tend to be more organized. We use the example of a procedural telephone versus an object-oriented telephone, remember? So the procedural telephone looked like a big pile of wires that just happened to be a telephone. When we look at it, we see all the details that we don't need to work with, plus all the things that we actually do need to interface with. In a procedural language, all of it's out there just for everybody to see. In an object-oriented language, we have an additional tool for organizing things. We can stuff all those wires into this box, then poke little holes so only the handset and the buttons we need to interface with for that phone are actually exposed to us. Then we can pass it around as a phone, an actual object, instead of dragging piles of wires around. All right, so object-oriented languages are closer to the way that we think about things in real life. All right. 2 kinds of programming languages, interpreted versus compiled. So we said interpreted languages are relatively slow, compiled languages are relatively fast. As you might guess, interpreted languages also tend to be loosely typed languages. Compiled languages also tend to be strongly typed languages. So that fast and slow stuff goes together. We talked about the computer program known as a compiler. So this guy converts high-level code, so the code we might write as humans, into the equivalent low-level language. So for instance, if I'm writing hello world for an Intel processor on a Linux machine, and I write it in Java, it might convert, or the compiler might convert our code into something like we looked at last time, the hello world assembly language program. All right, so then we started talking about the evolution of languages, kind of how we got to where we are today. And we drew a picture here. So, 1968, we had our kind of what I called our first programming language that's meaningful to us today. C is nowhere near the first actual language. From there, we went to C++. So this was a procedural language. This was an object-oriented language. So we can throw that in here. All right, now remind me, why did it take 15 years for us to decide that procedural languages, that the pile of wires that equal a telephone, was no longer going to cut it and we finally need something more. Why did it take 15 years to get to that point? Wouldn't it have taken us about 5 minutes as a human if you had to pick between the phone that looks like a phone and the pile of wires that looks like a pile of wires that's actually a phone? Wouldn't 100% of us pick the phone, the thing that looks like a phone? So why did it take us 15 years? Why? You're right. So, but why is that? Why was there no need?
There are no complex codes and everything during that time.
Okay, so
15 years, the code became more complex.
so in those 15 years, so if we say 1968 was kind of the early years of computing, right? So as computer programmers were writing software, the software they were writing between 1968 and 1983 was, relative to what we view as a computer program today, very, very simple, right? They were much closer to your Hello World program than they were to Grand Theft Auto. They were much simpler programs back then because we didn't have the power in the computers that we have today. And we also didn't have, because we hadn't integrated computers into all parts of our lives, we hadn't used our imagination to think of all these different things we might use computers for. Make sense? Okay, so between 1968 and 1983, probably it was really between 1968 maybe 1978 or something like that, when we really weren't solving problems. Then between 1978 and 1983 is when we were trying to kind of make do. That's when we started running into those situations where the problem I'm trying to solve is a little bit too complex for C, so it's kind of unwieldy to solve the problem with C. And think about that like fixing things around the house. Sometimes you don't necessarily have the right tool for the job, but you can usually still get it done with enough duct tape and screwdrivers and things like that. But you're not necessarily using the appropriate tools for the job. Make sense? So we were kind of duct taping things near the end of the C, the C life cycle before C++, even though C is still used today. We'll talk about that in a little bit. Okay, so we talked about the evolution of C. Specifically, it had variables. It had a single name with a single value. It had a collection of like values. It had this thing called a struct, which allowed us to hold a collection of things that were not necessarily the same kind of value. So for instance, we can hold a first name, a last name, and an age, that kind of stuff. We looked at an example of that here. Here's our first name, our last name, and our age, and our struct, so how those things might work. And then we decided, as we start moving towards an object-oriented language like C++, which we show over here, we can move these external functions into our organizational tool here called the class. So now this class doesn't just hold a couple of strings and a number. Now the class holds a couple of strings and a number as well as a function. Okay, so it's more general purpose. We can put more stuff into that container. So what did C++ do? They kept the variable, they kept the array, they kept the struct, but they introduced this new thing called a class. We still had our procedures and functions, but the problem with our C++ programming language mostly had to do with beginning programmers, people who were just starting to learn how to program, and that's that it empowered programmers to make unwise decisions. And the example we used last time is in a language like C++, if you were inviting somebody to your house for the party, you could hand them the house instead of the address where the house lives. Makes sense? And in real life, that never makes sense. And we could say in the programming world, the reality is it very rarely would make sense. So I think the number I probably used last time was something like about 85% of the time, the way we solve problems in the programming world will be identical to the way we solve problems in the programming world. Or real world and programming world will be the same 85% of the time. It's that last 15% of the time that every now and then in our computer programming world, we might need something to work, or it might benefit us to make something work in a different way than it might work in real life. Because in real life, we are limited by real rules. Things like gravity and like lifting a house is going to be a problem all the time in real life. Well, in a computer program, The weight of a house is actually just its memory footprint, right? It's the amount of memory that house might take up. Oh, well, with that said, a lot of our computers have a lot of memory in it. So if you have 16 gigabytes of RAM in your computer, yeah, it might not be the most efficient way of dealing with the house, but you could pull it off if you needed to. Or in real life, none of us are lifting houses. Okay, it's just not in our wheelhouse, pun intended, I guess. All right, so a problem with C is it allowed beginning programmers to accidentally make poor decisions. I think that's the bigger thing. So C++ is still a pretty popular language today because it allows advanced programmers a lot of control over what they want to do. If they want to pass something by address, if they want to actually hand somebody the address of the house, they can. If they want to actually hand somebody the house, they can do that as well in C++. And if you know what you're doing, you have a tool that's very flexible. But if you don't know what you're doing, now all of a sudden you have a tool that can get you in trouble pretty quickly because you're still learning. So that's kind of where Java stepped in. We talked about pointers last time as well. It's a variable type for holding memory addresses. So evolution of Java, we have variables, we have arrays, we have our class, but we dumped structs. Anybody remember why I said that was a bad idea? Java got rid of structs because they effectively said that, you know what, a struct is effectively a class that the programmer chooses not to write methods in. Not to write functions, methods, procedures, whatever you want to call them. But is that really the only difference between a class and a struct? Is a struct literally identical to a class that happens to not have procedures in it? Why? Why are they not exactly identical? How are they different? Talked about it last time, right? Could have a quiz on it. Did that go well? Did the quiz go well? No. Is that a no? Go ahead.
Structs possess the object with references and class possess the objects with value, or is it vice versa?
Okay, so which one passes by value?
So passes by value is classes.
Okay, and the other one passes by reference. Okay, it's the other way around. So a struct, by default, is passed by value. A class, an object, is passed by reference. Okay, so in a language like C++, if you were to build a struct and you were to hand that struct off to a procedure, you're passing it the actual house, okay, the actual thing. If you had an object, a class, and you passed it, it's always being passed by reference, by default. All right? So even though these two things might look identical to each other, they're not actually identical to each other. Okay? Even if they function the same way, if I pass this guy without doing anything special, he's passed by value. If I pass this guy without doing anything special, he's passed by address. So they are not identical. Every now and then, that difference might make a difference. Okay? So Java dumping a struct really creates a problem. And this is something I don't think we did talk about last time, and this is really a problem with how modern programmers are taught, and kind of the reason why I teach classes the way I do. Computer programming today is often taught in a much more applied way. So rather than learning the fundamentals of what's under the hood, how do these languages work, things like that, you instead just learn how to do stuff. And you never really necessarily understand how that stuff works. So if we take a modern programmer who learned in Java, but didn't really understand why certain things work the way they work, and then all of a sudden they get a job someplace, they transition to a different technology, their only reference point is how something worked in Java. And they might think that's how it works in programming. When the reality is Java's delivering them a very filtered version of what programming is. All right, so understanding what came before that is pretty important when it comes down to actually becoming a good computer programmer. Focusing on computer programming is a skill set where the language doesn't matter. All right, so besides getting rid of the structs, they also removed the special syntax for pointers. We talked about that last time, this star stuff and ampersand stuff. I think we looked at some examples of that. So Java got rid of that, so we didn't have a special syntax for dealing with pointers because Java made all those decisions for us. They decided what's an address versus what's a value. Okay, so near the end of class last time, we started talking about the evolution of C#. Okay, so this guy, if we look at it in our chart here, we see it came out kind of midway through, it's almost equivalent to Java, but it did come out after Java. So C# kept the variables, it kept the arrays, it kept the classes, it kept the procedures and functions, but it brought back a special syntax for dealing with memory. But you had to do it inside of this unsafe code block. All right, so C# looked at Java and said, you know what, we think Java does a lot of things right. But the one thing they did wrong is they completely took away from the programmer the ability to deal with memory. So instead, we're going to go ahead and we're going to say, look, if you don't do anything special as a programmer, we're going to make the right choices for you by default. Now, if you want to prove to us that you know what you're doing, that is, you're going to specifically create a code block called an unsafe code block, then we will go ahead and we will allow you to use the old style C and C++ syntax for working with memory. Okay, so C# brought that back to the table. Make some sense? Okay, so we have Java versus C#. Now remind me, what was your paper on for today? You had a paper due today, right?
Yeah.
What was the paper?
It was on the differences between Java C#, and Objective-C.
Okay.
In the career path of Java.
Okay. So before we get into too much of my material for this, tell me, what did we find out about Java versus C#? Forget about Objective-C for a few minutes. What's the difference? We all wrote like a 2 to 3 page paper on this, right? What we get?
Was for only some particular operating system, like Microsoft only.
For C#?
Yeah.
Okay.
Java was platform.
Okay. So you want to say that Java is platform independent. Okay. Now, if you talk to the Microsoft people, they're going to say that's platform independent as well. Okay. Yeah, but you're right. You're right. What else did we find out between Java and C#? I'll clarify this in a few minutes.
Java has two kinds of exception handling, checked and unchecked, while C# has just one type of exception handling.
Okay. Tell me about C# exception handling. You said Java has two kinds. What were the two kinds Java had?
Checked and unchecked.
Checked and unchecked. Okay, what's the difference between those? One had the word checked in front of it, the other one had the word unchecked in front of it. So you found a difference without really finding out what the difference was?
I was going to ask you after the class.
All right, what else did we find?
C# is more complex language than Java.
Okay, tell me about that. In what way is it more complex?
I just found the difference. I did the differences. Like, I didn't know the reason why, but I just found the difference.
You just wrote it down. kind of an open-ended thing, right? Like, oh, it's more complex. That's like saying a Ford is more complex than a Chevy. What does complex mean?
Java didn't have, is you like Ragnar mentioned, they don't have the pointers. And C Sharp have took like both features, value as well as reference,
Okay.
user-friendly value.
So I suppose with that in mind, if we're going to say they're relatively close in complexity, because C Sharp brought some stuff back, they had to add in facilities to allow the programmer to make some decisions that Java didn't. So you can make an argument that C Sharp, because of that, is slightly more complex. Did you make that argument? You didn't make. You just put this more complex thing. Just wrote that down.
Like I did read it, but I forgot what it is. I did read it once. It's just once.
I saw that Java is more vulnerable to security threats
Okay.
because it's platform dependent.
Okay. I think Java being more vulnerable to security threats could be a true statement. You said it's because of its platform independence.
Yeah.
Okay, why would that make it more vulnerable?
Because I guess because it's an open source programming language, I guess.
Okay, I mean that there's probably truth to that as well. So one thing is Java's open source. So and you're kind of saying that it's you know, more vulnerable to security issues. All right. The open sourceness of Java probably does make it more vulnerable to security issues. It probably also makes it more available for security patches.
Right. That's the argument I made that because it's platform independent, it has its positives and negatives.
Mm-hmm.
And there is a community there is more Java libraries out there because of how open source it is.
Mm-hmm.
So it really enables programmers to be faster.
Now, if you look at who are the people writing the security vulnerabilities, the hacker people, right? The bad people write viruses and crap like that. Well, on the flip side of that, you can have IT professionals who can also go and look at the source code of Java and look at ways of making it, more secure, right? Just before I came over here tonight, my wife, we came home from our trip earlier in the month, and we had found a mouse in the house. And so that guy's gone, but so she brought in a handyman to go and check around the house. So, you have the mice, the evil mice that want to get in to the house. Well, now we want the handyman to go up and patch any places where the mice can get in. And they're both looking at the same house, right? Mice are looking around the house on the outside, looking for the holes to get in. Handyman's on the inside, looking for the holes that they're getting in from, and he's patching those up. So when you have an open source programming language, or any open source software, you have both the good and the bad people looking at it. So good people can look for those vulnerabilities, bad people can look for the vulnerabilities and try to take advantage of them before the good people get them patched up. So it probably goes a little bit both ways. All right, anything else you want to say about Java versus C Sharp?
There is one.
Okay.
C Sharp is grouped in like namespaces, whereas Java uses packages.
Okay, that is a true statement. How are they different? Another one of your magic bullets. Yeah, so it's kind of an organizational structure. Java has something called a package. C Sharp uses something called the namespace. At the end of the day, functionally, they work pretty similar to each other. They give you a means of adding, we'll talk about variable scope here before long, but a way of adding a scope within your project. So it's kind of maybe different approaches to the same problem, but they're pretty much the same. Let me go this route. So you mentioned that Java is platform independent. How does it do that? Well, first of all, what does that mean? What does it mean when we say Java is platform independent?
Can work on any operating system on every machine.
Okay. So it can work on Windows, it can work on the Mac, it can work on Linux, so on and so forth. Okay, how does it work that way? Why is it able to run on all these different operating systems?
Was it converts a high-level language into bytecode?
Okay, so what gets converted into bytecode?
Actual code, Java code.
Okay, so Java code gets converted into bytecode. Okay, tell me about bytecode.
Bytecode is a WF language.
Okay, and so is it?
Like every other platforms.
Okay, so bytecode is an intermediate language, kind of like the assembly language we've looked at. So it's kind of like a low-level language. Okay, that still doesn't tell me how Java accomplishes its platform independence. I agree that your high-level Java code gets translated, gets compiled into a low-level bytecode called Java bytecode. I'm cool with that. How does that help it be platform independent?
It's because of the Java virtual machine.
Ah, Java virtual machine. Tell me about that.
It converts the Java code into assembly language.
The bytecode.
Yeah.
Okay, so the bytecode. So Java virtual machine, this guy is implemented for each platform that Java is, let's see, each platform with which, let's use good English, Java is compatible. So that means that somebody wrote the Java virtual machine for Windows. They wrote the Java virtual machine for the Mac. They wrote the Java virtual machine for Linux, so on and so forth. Now, each of those guys, the Java virtual machine itself, as he pointed out, at runtime, we're going to say this guy kind of interprets Java bytecode into native assembly code for that architecture. All right, so we have that intermediate language, a low-level language, and every single Java virtual machine, which is a computer program, knows the same Java bytecode, right? So I can compile my program on Windows, and I can then take it over to a Mac, and I can run it on the Java virtual machine on the Mac, and it's going to understand that bytecode, because the Java virtual machine was written to understand Java bytecode. Okay, Java bytecode is independent of the platform it's running on which it's running. But the Java virtual machine for Windows, while functionally equivalent to the Java virtual machine for the Mac, while functionally equivalent to the Java virtual machine for Unix or Linux, each one of those guys has ported, is a port of the original Java virtual machine, so they have to accomplish all the features, all the things the Java virtual machine knows how to do on that particular platform. Make sense? So we can say not all JVMs are created equal. Not all JVMs are created equal. Okay, so if I have a Java program that I wrote once, and I go and run that program on Windows, and I go run that program on the Mac, the program is actually running on two different Java virtual machines. These guys are functionally equivalent to each other. They do the same thing, but the means by which they do it might be a little different. So for instance, a Honda motor might work a little bit different than a Ford motor, but they both make a car move, right? But the mechanics within it, the way it actually accomplishes it, one might be a little bit more efficient in one way, one might be a little bit more efficient in another way. They ultimately solve the same problem, but potentially in a slightly different way.
So what does it come with? Does it come with the machine or
The Java Virtual Machine is a computer program that you would download off the internet.
okay.
So now it's Oracle, but the original was Sun Microsystems, people who originally made Java. You would go to them and you would download the virtual machine for your platform, either Windows or Mac or Linux, and you would say, okay, well, I have it for Windows now, and here's the, this is the scoop, and you would run your program on it, and from your perspective, for most applications, because a human being's not going to be able to tell the difference, we're not going to be able to tell the difference between 4 nanoseconds and 20 nanoseconds, right? So from our perspective, for most things, even though they aren't necessarily happening identically, just like you can't tell between 2 or 3 horsepower in a motor, they aren't necessarily implemented identically. That makes some sense? All right, so we are at the mercy of the implementation of the virtual machine for that particular platform, but the hope is for most applications that isn't really a problem. Okay? All right, so it's platform independent. Then let's go this route. I'm actually going to draw a couple of pictures here. I think this will be helpful for us. So Java source goes through the compiler, turns it into Java bytecode, which then is interpreted by the Java virtual machine. Which then runs natively. Well, here, let's just say, do something like this. CPU. Reorganize this a little bit. So let's do that arrow on this side. So the Java bytecode gets sent into the Java virtual machine, which then gets interpreted on a one-to-one basis, mapped over to the CPU, and run natively on the CPU. All right, so this is how Java actually works. So what makes Java platform independent? Rather than us as the programmer having to rewrite our program for Windows and rewrite our program for Mac and rewrite our program for Linux, we instead write our program one time, we're writing it for the Java virtual machine. Then Sun Microsystems people, now Oracle, they wrote the virtual machine multiple times for those different platforms. All right, so now on the surface, is platform independence a good thing? Would you call that is that something that makes Java better? You think? Okay. Any downsides to it? You mentioned that C# isn't platform independent, or at least not as overtly platform independent. So platform independence must not be perfect. Just looking at this diagram here, you see any weaknesses here? Or at least, let's say, potential weaknesses?
So many pages to go through.
Okay. That's true. No, yeah, the more hoops you have to jump through, maybe the more time something takes. Are any of these hoops specifically concerning? Last time we talked about compiled languages versus interpreted languages, right? And we said compiled languages are relatively fast, and we said interpreted languages are relatively slow. Now, we happen to see both of those words on the same exact chart here. So we have the relatively fast word as well as the relatively slow word all in the same pipeline that's leading to your Java program running. So we have an issue here. And that is the Java virtual machine itself is a piece of software. So our program at the end of the day is actually being interpreted. Hopefully it's a pretty fast interpretation because it's on a one-to-one equivalence with actual magic tricks on the real CPU, right? We aren't having to take a high-level language and convert it into all the equivalent stuff. But, you know, the reality is that there is some time. It takes some time, right? We do have to do some conversion, and that slows things down. Now, for most applications, we might say it doesn't slow things down enough for a human to be bothered. We could say that, right? But for some applications, maybe it would. Any applications that you can think of that speed is of the essence? Where we would notice a slowdown? What do you think, GTA? It's Grand Theft Auto. It's apparently his game of choice. How would you feel if your video game was a little bit sluggish? You wouldn't be happy. Yeah, you're not happy about that. So when you play video games, you want them to be fast. So games are one of those applications that rely on performance. Now, you play on console or do you play on PC?
Some games I play on console, some games on PC.
Oh, so both. So you basically don't have a life. You just play video games. I mean, that's it. That's the end of the day is your video games, right? Yeah, that's kind of it. What did you do today? Tell me about your day.
Yeah. He got up at 2 p.m.
Okay, you got up at 2 p.m.?
Yeah.
3 p.m.?
No,
What was he doing all night? Playing video games?
No, I was concentrating on the assignments.
Okay. So I was concentrating on the assignments and in the game. So you were chatting with fellow gamers about your assignments.
Usually I do my assignments on another laptop.
So you're not persuaded to play. How many hours a day do you play video games?
Just like 2 to 3 hours.
Except for days that end in the word day? Except for days that end in the word day?
A day has 4 parts. So every part he plays 3 hours. A day has 4 parts, right? So he plays 3 hours a day.
Per part. Per part. Okay. I get it. Okay. So in any case, well, hopefully that was a good one. You might not be able to notice, but I'm not feeling so hot up here. So I'm looking forward to our first break. We'll see how things start turning. But in any case, you want your video games to be really, really fast, right? So if you notice any sort of slowdown, you're going to complain. It's not good for us. So Java, one of its original motivating factors was that, hey, video games are coming out for PC, but not coming out for Mac. So if we had a new technology like Java where the game makers can write the game once and it comes out for both, then everybody's happy. And kind of 2 problems with that. One, as we already said, we want games to be fast. 2, the only people that were really complaining that games are coming out for the Mac or coming out for PC and not for the Mac were the Mac users, right? And what percent of people use the Mac versus use the PC? A very small percent, right? So really you had this little tiny crowd that was screaming, and the people perceived that it was actually a problem. If you're a video game maker, you're going to rate your game for the 97% of the people or the 2% of the people? The 97, I want their money. I don't care about their money. They're just going to complain anyways. They're Mac people. They're just going to complain. All right. So if we take this same picture, so that doesn't mean this is bad. It just means that this is only reasonable for certain applications. Mostly business, cross-platform business applications, that kind of stuff. All right, so now let's look at how C# did this. Now originally, and we'll go into more detail with this later.
Question.
Sure.
So is Java actually a compiled language or interpreted?
Yes. It's compiled first and then it's interpreted right before runtime. And I think you'll see here when I make the comparison with C#. So C# goes through a compiler, which changes this guy. Anybody know what language the C# compiler converts C# into? Probably should have made your paper. Recognize that from any of your reading? Microsoft Intermediate Language. This might as well be Java bytecode. Same thing. All right. Then, instead of running in the Java virtual machine, this guy runs through something called .NET. Then, instead of interpreting this, we use something called a JIT. Anybody know what a JIT is? None of this came up in your research? Thought you said you were focusing on your homework. No, you weren't focusing on your homework. You're playing video games.
I didn't start researching.
Just-in-time compiler. So JIT is a just-in-time compiler. All right, so what this does is right before you run the application the very first time, this just-in-time compiler takes this missile code and converts it into native assembly code for this CPU. So the very first time you run the program, it's going to take a little bit longer for it to start running because it's doing that conversion. But it only ever has to do that conversion once. From that point forward, when you run that program, it's running natively on that CPU. Make sense? Okay. So we're going to say that between the two of these, C# made some choices that made it faster where it counted. Okay, because instead of interpreting, which is slow, they decided, look, we'll be slow the very first time it runs, before it runs, but then from that point forward, it might as well have been written in C++. It'll be fast. That seems good. At the same time, the Microsoft people would say that C# was platform independent, even though she pointed out it's not. They would say, you know what, C#, it's awesome. It'll run on any platform at all, as long as it supports the .NET component architecture, which is basically them saying it'll run on any platform as long as it's Windows. That's effectively what they're saying, right? So, with that in mind, it's problematic. Let's say that much. Both of these languages are still popular today. Java has its niche in the cross-platform business applications, specifically things that launch out of web browsers. C# obviously has its niche on anything Windows, native applications for Windows. C++ has its niche, where's our picture here? for game programming. And C still has its niche for embedded systems because it's a much lighter weight language than C++, so you can fit it on smaller embedded systems for making little microcontrollers do stuff. So it's not completely gone anymore. Okay. Now let me check something here. Actually,